Instead of drawing my little circuit all over again, I'm going to use the same image that we had from the previous video to just show you that simple circuit. So if we're looking at the idea of the simple circuit, we can focus in on this. What we're going to actually be looking at here in this section of conduction, insulation, and protection, it is basically the fail-safes that different components within a circuit have in order for them to conduct electricity or electrical current, for them to insulate against potentially, harming or destroying the material that the circuit is embedded in or the people handling it, and basically finally fail-safes that we've actually devised to go into circuits to make sure that they don't actually hurt us. So the first idea here is the idea of conduction. We've been talking since the beginning of the year about materials that will conduct electrical current. So the idea of conduction is essentially transmitting that electric current that's coming out of the battery from point A to point B. And we do this with the help of wiring. Okay, we know that wires, so if I look here and I'm going to draw this, we've been playing around with wires for a while now, and we know that wires always come in those multitude of colors, right? And they always seem to have these plastic casings around them. And I mean, other than looking pretty, we don't really realize that they do have another actual, reason behind it or purpose. And we're going to talk about what that is when we talk about the fact that the vast majority of the wires that we have are basically pieces of metal that are coiled around one another. That metal is often copper. Okay. Copper is an excellent conductor. And what ends up happening here is that as copper inside the wiring is conducting electrons along the wire from, let's say, the battery source in our first diagram. So from that actual source all the way through to the actual light bulb, okay, we have to get the current going from the battery to the actual light bulb. And if we use a certain material that is not a conductor, those electrons aren't going to go anywhere. We've got to use something that likes to push electrons along. And that ends up being metal. Okay, metals are excellent conductors. Now, the reason for this beautiful plastic often coating around wires is not only because the wiring, because it keeps the metal together and it keeps it from fraying, but it also prevents those little electric currents inside the wiring from leaving elsewhere. Okay, it focuses the current and it makes it move in a certain direction. This is why our current is forced to flow through the actual object and along until it gets back to the power supply. It's because of the fact that we've used a very conductive material and we've actually insulated it and forced the electrons to actually follow along the metal. They don't go anywhere else. So if we just had this metal, all right, if we just had this metal here and nothing else, if we had a bunch of wires, okay, that were just sitting here like this and bits were fraying out, kind of like split ends in a hair, well, some of these electric currents and these electrons that were being transported along could actually not make it to their final destination and go elsewhere in this circuit. And that would actually lower the efficiency of our overall circuit. So if we look at the idea of our insulators, let's go back to our little split end piece of copper here. The fact that insulators surround these conductive wires prevents this idea right here from happening. It prevents loss of these electrons from going elsewhere other than where they're intended. Now, we'll usually see that insulators are made of a lot of times plastic or rubber because they don't conduct. They're very, very poor conductors. The final safety precaution of a lot of circuits has to do with the idea of embedding, and we see this a lot in homes and large appliances or buildings. We'll see the idea of embedding a protective device that should the circuit have too much electrical current going through it, there's a fail-safe there that will trigger the stopping or the breaking of that actual, full-on closed circuit. So the idea of protection or a protective device inside a circuit that automatically shuts the circuit down should there be an actual power surge, too much power going through the actual circuit. And the two main forms of protective devices are known as fuses and breakers. So we're going to look at both of these individually. We're going to start off with fuses. So the idea of a fuse, fuses are actually quite small, and this is just one type of fuse. You'll often see fuses in older appliances like stoves, washers, dryers, anything that uses a great deal of electricity. Nowadays, we tend to see a lot more of, the idea of breakers in homes. But in older homes, there will be a fuse box where a variety of the fuses are contained. And what a fuse is it's basically a component that's added to an actual circuit. So if I have my circuit here, okay, and then we keep going, and let's say I have my resistor here. So I've got my light bulb. What ends up happening here is the power actually leaves the negative side, travels down, goes through, lights the light bulb, and as it makes its way through the fuse, this little gray wire here is often made of a very malleable and like easily melted metal. Sometimes things like aluminum or other kind of soft and pliable metals. And what ends up happening is if the current or the amount of energy going through the circuit is acceptable, that metal will hold fast and it won't take any energy from the circuit. It will just allow the current to flow through it. But if something happens that there's too much power going through the actual circuit, it's on overload. What ends up happening is this little metal here will actually basically break. It will melt and it will cause a disconnect within the actual circuit. So there will be a piece here and a piece here. And so this opening right here, this amount of space right in between here, will not allow the circuit to go through. So that's where the concept of blowing a fuse comes from. Okay? If there's too much energy or current going through the circuit, the fuse is there as a fail-safe, and if that little piece of metal melts and breaks, then it shuts off the fuse automatically, or it shuts off the circuit automatically, and it forces you to replace the actual fuse. The same sort of concept is applied to the idea of a breaker. So the idea of a breaker, and the difference between a breaker here is that breakers can automatically be turned back on. They can automatically be reset. Whereas a fuse in a system has to actually physically be replaced. If the fuse is blown and you don't have any other fuses, you won't actually be able to turn that circuit back on. Whereas a breaker will let you actually just switch the actual object back on. Now, what ends up happening in a breaker is you have what's called a bimetallic little piece of metal right here. It's kind of bendy. And it's usually made of a couple types of metal. That's an alloy. And what ends up happening is when it gets really hot, it basically changes its shape. And as soon as it changes its shape, it ends up basically moving away from the surface here. Okay, it makes a little bit of a gap. All right, so we'll just turn this a little bit like so, and it moves away. All right, and what ends up happening here is that this is connected to the actual circuit. It's part of the actual circuit. And as soon as there's a space here, that connection is broken. The circuit is turned off. So this actual button gets shot off over to the off side. So you can go look at an actual breaker box and it will be listed what breakers are for what appliances or what actual parts of the home. When I was at grad school, my roommate and I lived in a really old apartment, and if she was using her hair dryer in her bedroom, I couldn't use the microwave, the toaster, the kettle, anything in the kitchen, because that was too much actual demand of electricity, and it would cause the breaker to always turn off. So what would happen if all these things were plugged in? We would actually it would almost be like there was a power outage in our house, and we'd have to go to the breaker board and turn the actual switch back on. Now, this works with the idea of an electromagnetic, current, in that it uses the actual idea of magnetism, and as soon as these objects touch one another and are attracted to one another because they're both ferromagnetic, it acts as a close for the circuit. It causes, once they're attached together, current will flow through them. And when the breaker is thrown off, they separate. Okay? So these are two types of protection for circuits.